Let's now consider a slightly more complex example involving three different functions and apply the Quine-McCluskey method we just studied. We will perform the synthesis twice, first using cardinality as the cost function, and then using the number of literals. Here you can see the prime implicants obtained during the prime implicant generation phase. I'll leave the calculation of these as an exercise for you. Let's begin with the synthesis using cardinality as the cost function. We build the prime implicant chart by placing the columns corresponding to the minterms of each function side by side, followed by the cost column at the far right. Since we are using cardinality, each implicant has a cost of 1. We now apply the essentiality criterion. I've highlighted in orange the X marks that identify an essential implicant for a given function, specifically when no other X appears in the same column. P5 is essential for F1. P1 is essential for F2, P0, and P9 are essential for F3. We add these implicants to the cover sets of the corresponding functions. We then update their cost to 0. The next time any of these implicants is selected for a different function, there will be no additional cost, as the corresponding AND gate is already instantiated. Next, we apply the row dominance criterion. P0 dominates P6. Both cover the same minterms, but P0 has a lower cost. Then P7 dominates P3, because with equal cost, P7 covers a superset of the minterms covered by P3. As a result, we eliminate both dominated rows from the table. We now apply column dominance to simplify the table. In F1, minterm 5 dominates 7, since 7 is covered by a superset of the implicants that cover 5. Then, minterm 8 dominates 9. In F2, minterm 2 dominates 3, 10, and 11, and minterm 6 dominates 14 and 15. We can now eliminate all these dominated columns from the table. We can now identify a secondary essential prime implicant for F1. Minterm 8 is covered only by P0. We update the cover set for F1 by adding P0. Next, we apply row dominance. P4 dominates P2, and P8 dominates both P7 and P10. We remove all dominated rows from the table. Let's complete the application of dominance rules by analyzing the columns. Minterm 13 dominates 15 in F1. Finally, we identify secondary essential prime implicants. P4 is essential for F3, so we update its cost accordingly. We also update the cover sets to reflect this new selection. No further simplification can be applied to the current table. The table is therefore cyclic. We now proceed using the branch and bound method. The adopted strategy is to first find a complete cover for F1, followed by a complete cover for F2. Implicants are selected in ascending numerical order. We start by selecting P1 for F1. Next, we select P4 for F1, which completes the cover for this function. Note that the cost of these selections is 0, since both implicants have already been chosen previously for other functions. We then move on to F2, starting with P5, and finally select P9, which completes the cover. At this point, we reach the first bound with a total cost of 0. Since the bound is already 0, which is the minimum possible cost, any further partial or complete solutions will not improve upon it. Therefore, we prune all remaining branches. Finally, we add the 4 implicants identified through branch and bound to the cover sets, completing the solution. Let me conclude by showing you the final cover sets. These are the expressions that describe the circuit, where 5 AND gates are shared across the 3 functions. And here is the final cost of the solution. 8 generic gates with any number of inputs, or 15 two-input gates. Let's now go through the same example a second time, but this time using the number of literals as the cost function. In the construction of the initial table, only the last column, which contains the costs, has changed compared to the previous execution. Let's now apply the essentiality and dominance criteria. The selection of essential prime implicants does not depend on the cost, so it is exactly the same as in the previous case. We select P5 for F1, P1 for F2, P0, and P9 for F3. We then update the costs of the selected implicants. In this case, the cost is updated to 1, since selecting the same implicant again will only require adding a single 2-input OR gate to the circuit. Finally, we add the selected implicants to the coverage sets of the corresponding functions. Let's now evaluate row dominance. P0 dominates P6 and P7 dominates P3. Note that it's just by coincidence that we found the same dominance relations as in the previous case. Since the implicants now have different costs, in general, dominance relations may change compared to those found using a different cost function. Now let's apply column dominance. For F1, 5 dominates 7 and 8 dominates 9. For F2, 2 dominates 3, 10, and 11, and 6 dominates 14 and 15. Just a quick reminder, during column dominance, we are not selecting any implicants to add to the cover set. We are only simplifying the table structure. Next, we select the secondary essential prime implicant P0 for F1. We update the cover sets accordingly. We then proceed with row dominance. P4 dominates P2. P8 dominates both P7 and P10, and P11 dominates P5 and P9. Note that, as mentioned earlier, the dominance relations differ from the previous case because the implicants now have different costs. We now apply column dominance. In particular, minterm 13 dominates 15 in the first function. We then identify new secondary essential implicants. P4 is essential for F3. We update its cost to 1. P11 is essential for F2, but we do not need to update its cost as the corresponding row will be eliminated. Finally, we update the cover sets accordingly. Once again, we reach a cyclic table. We proceed with the branch and bound method, which, as you'll notice, is applied to a single function. We select P1 and then P4, reaching a bound with cost equal to 2, which cannot be further improved. Therefore, we add the 2 selected implicants to complete the solution that was previously obtained. To conclude, here are the cover sets, the expressions that describe the final solution and the cost, which amounts to 8 generic gates or 14 2-input gates. As expected, using different cost functions can lead to different solutions, unless the result consists only of essential prime implicants.